emitter bias circuit. The difference between this one and the previous one is, if you notice, this one has an emitter resistor. So adding a resistor to the emitter circuit stabilizes the bias circuit. This is the input side of the circuit, and this is the output side of the circuit. Okay, where RE is common to both input and output. So I'm going to focus on the green part first. So I can redraw the green part like this. Okay, so this is all the green part, input loop, and I'm going to apply KVL here. So I'm again starting off from here. Okay, VCC minus IB RB. Okay, so this will be IB, not RE, IB RB. Okay, and then we have plus minus here VBE. So you have minus VBE, and then you have this resistor right here, okay, which is RE. The current flowing in this is emitter resistance, IE. So you got IE and RE equals to 0. Okay, so that's your equation. IE equals to IC plus IB, correct? We know IC is beta times IB plus IB. And if I take IB common here, I get beta plus 1 times IB. That's equivalent to IE, correct? I'm going to replace this IE with this value. So I can take IB common. So that's what I did here, replacing IE with beta plus 1 IB, okay? And here I took IB common. So if I rearrange this equation, it will be, say, VCC, and this is minus VBE here also. VCC minus VBE equals to IB RB plus beta plus 1 times IB RE, okay? And in this two terms, if I take IB common and find out the IB, I'll get this equation right here, okay? Everything that comes out common goes over here to the denominator, and that's what we have over here, RB plus beta plus 1 RE. If you remember, in the previous configuration, we didn't have this term. We didn't have this term over here. But now in this configuration, which is the emitter bias configuration, we have beta plus 1 times RB. And I want you to think of it in a way that beta is an amplification factor, right? Which is usually in the range from 90 to 400. And this value changes is dependent upon temperature. We want to make or do things such that it is temperature independent. What we can do in this equation, or what value we can choose for RB resistance and RE resistance such that beta does not have too much of significance. Okay, so I want to throw you something. I'm just going to take a denominator here, okay? RB plus beta plus 1, okay, times RE. Let's say I choose RB. Let me change the color. Say RB is 75K. Beta is 90, so 91. Okay, 90 plus 1 is 91. RE is 1K. You have 75K plus 91K. Does this beta gonna have a significant impact upon this term?
It has a significant impact.
Yeah, because beta is beta plus 1 times RE. This whole term has a magnitude of 91K, right? And this is 75K. So this 91K has more impact upon 75K. Ideally, you want this RB, this term over here, to be so big. Like if this RB is like 100K and this beta plus 1 times RE is, say, 2K or something, beta plus 1 times RE, then if you plug in the values, you are basically doing 100K plus 2K. And because this term is so bigger and this term is so smaller, this term has a significant impact. And because this term here has a beta factor in there, because this number being small, beta, even though it may change, it's not going to have an impact upon this magnitude. We want our RB here, we choose values such RB is bigger, and then this factor is smaller, okay? And because as a designer, we have the option to choose the values for RE and RB, we do pick up those values which make this term bigger. That's where we can take the beta and make it temperature independent, okay? Now this is the collector emitter loop, again output loop. Here we can uh, redraw the circuit like this. So this is the circuit here. Starting from here, VCC, you have VCC minus ICRC minus IC minus ICRC minus VCE, which is the voltage across this, minus VCE, and then minus this resistor right here. The current is IE times RE. IE times RE equals to 0. In this equation, remember IE is approximately equal to IC, right? So I'm going to replace IE with IC in this equation. So VCC minus ICRC minus VCE minus ICRE equals to 0. And if I want to find out the equation for VCE, then I get VCC minus, and I can take IC common between these two terms, ICRC plus RE. So that's what I get as an equation for VCE, okay? VCE. Okay. And if you look at this equation, they have the same equation over here. VCE equals to VCC minus ICRC plus RE, okay? Also, remember folks, VE, which is the voltage across the emitter resistor, okay, equals to IE times RE. This I have already told you. VCE equals to, you look at the subscript, so VC minus VE, okay, and then from here, if you want to find VC, that will be equals to VCE plus VE, and that's what this equation is, okay, right? So improved by stability. Stability refers to a circuit condition which the current and voltages will remain fairly constant over a wide range of temperatures and transistor beta values. Adding RE to emitter improves the stability of a transistor. Now we need to get the saturation, you do the load line analysis. So we need to do output loop equation, which is this right here. And I can rewrite over here, output loop equation, VCE equals to VCC minus IC, RC plus RE, right? Okay, and what we do with this equation, in this equation, we put IC, okay, we put IC 1 times 0, and when we do that, we get what? VCE equals to VCC, correct? And the second time we put VCE equals to 0, which gets us IC equals to VCC over RC plus RE. These two equations, VCE equals to VCC and IC equals to VCC, that's what we get over here. And that's what we got over here. And then we, based on that, we create a load line. This IBQ, how do we calculate it using this equation? We get IBQ, whatever that number is, say that number is 20 microamps. You just, wherever this load line superimposes on that IB, that will be your Q point. Okay. Now, again, you have much more flexibility this time to change your Q point. So say if you want to move your Q point to over here, what are you going to do in terms of VCC or RC plus RE? What you could do, say I want to keep VCC constant, I can change my RC plus RE. So the sum of it, you need to decrease it or increase it in order for me to get the Q point over here.
Increase it.
Okay, so if say RC plus RE is 2K, okay, if I change RC plus RE to 4K, and then if I draw the straight line, okay, it's probably not the very straight line, but yeah, there you go. Okay, so if I want to move my Q point over here, this here, RC plus VCC over RC plus RE, going with a value of 4K, will move point from here to here, and that would give me my new Q point, which will be over here. And then again, remember folks, this right here, which is your VCE, and this point right here, which is your IC, okay? These values should match with what you will get over here from these equations, okay? You know VCC, you will know IC, you will know RCRE, whatever you get VCE from your load analysis, it should also be close to what you get over there, okay?